again. We concluded the first part by introducing the properties of the stars. So now we are wondering indeed why we need to know the properties of the stars in these very in-depth details. Well, we need to know that because, as we're going to see, the star trackers are, so the star tracking assembly is made by or consists of optics, so that you need to filter the signal that you're receiving from the stars, and also detectors, so that, as will be seen later, it is usually made by CCD, so charge coupled device. But before going to the detail of the how the instrument is made of, we need to define what is the process that is used in the star sensor attitude determination software. So previously, I already cited one of the two of the first step that represents one of the critical steps. That is the load of the star catalog. So as I said, when you plan a mission, you already know what is the part of the sky that you're going to look at. So you need to load on your spacecraft, on your spacecraft system, the catalog map of the portion of the sky that you're going to observe. Why you need to know that? Because when you're going to match what you are seeing from your instrument to the catalog, that represents indeed your measurement. So in order to translate that in the BABA problem, what I mean is that your instrument give you the W, and the catalog give you your V. So the position of the stars in the celestial coordinates. By doing the by rotating these two these versor, so to the optical bench frame, you're able to get indeed this versor in the body frame. So what you need to know is the attitude. So you have these two versors that has to be compared in a certain way in order to provide the attitude of the spacecraft. So star catalog give you V, and W is given by the sensor. But in order to start this process, you need to identify the stars. So as I said, your star catalog has a certain number of stars with a certain magnitude and a certain spectral type. But you, for example, if you have a field of view of 5 by 5 degrees, you will have multiple stars with approximate similar magnitude and similar spectral type. So you have to be sure that when you're trying to compare what is seen by your instrument and what it is, what you have from the map loaded by the star catalog, are exactly the same. So the first process, it is indeed the star identification and acquisition. The second step will be the tracking of the star. So once you know that you recognize exactly where the stars are in your map, you are able to not always reload the catalog, but basically go in the tracking mode. So you are trying to observe how the stars is moving along your sensors in the sensors detector in order to follow the attitude. The other and the final step is the attitude processing and the refinement. So once you are able to compare the two, basically to follow the evolution of the position of the stars in your sensor, you can use different attitude algorithm, for example, the Quest algorithm, or as we are going to see, the extended Kama filter to reconstruct your attitude. So let's go to the details of the instrument. Here at the top of this slide, there are reported 3 types of star sensors. There are and those star sensors depends on the mission that you're going to design. For example, if you have a spinning spacecraft, you don't have a star sensor that is fixed on the spacecraft, but you have what is so-called star scanners. So basically, assuming that you have a spacecraft that is rotating along this axis, so basically the spacecraft is rotating along this axis, you have, for example, a star tracker over here that is scanning a portion of the sky. So you're not looking at the fixed region of the sky, but you are looking at you are scanning a certain area of the celestial coordinates. But the main star trackers that are used right now, and so in the last years, are the so-called fixed head star trackers. So it means that you have a spacecraft, as we have seen at the beginning of this part of the course, that is fixed on, for example, the optical bench frame. So you have a star tracker with an optical system that is looking at the sky. And you have also the possibility to have a much more complex instrument in which you have that the instrument itself, so the star sensor, is not fixed on the bus of or the optical bench frame of the spacecraft, but can move. And this movement is provided by gimbals. So it is called the gimbal star trackers. It means it is the same principle of the gimbals of antennas. So basically the instrument is moved by these gimbals in order to point specific portion of the sky. The advantage is that you are able to look at the region of the sky that are not, for example, invisibility if you are on a specific part of the spacecraft. The main disadvantage is it is more complex and usually is also less accurate because the movement of the gimbals can provide errors. So the design of the star sensors is so for all the 3 classes, but we are going to focus especially on the fixed head star sensors, is given by 3 main elements. As I said, you have the optics of the system, you have the light detector, that could be the charge coupled device, and you have the readout electronics that basically is given by the fact that you have a detector that will process the signal received by the star. So how this sensor works? First of all, you have to define a reference frame, because as we said, not only you have the optical bench frame, but you have also the instrument frame. So for the star sensor, you will have a star tracker reference system that is centered, for example, at the lens sensor optics of the star sensor. So in principle, when you have to determine the attitude, as I said, is the rotation matrix from the inertial reference frame I0F to OBF. Here, you have to be careful that in principle, you don't have, when you have measurement from the star triggers, you have an additional matrix that is the instrument, let's call the, how it was called, the beginning, just to use the same acronym. So the SCF, so the optical sensor coordinate frame, so the optical sensor coordinate frame, so SCF, to the OBF. What we can assume easily is that this transformation matrix, so the attitude matrix, will be indeed the product of this matrix and the ICRF and the SCF. So this is the optical coordinate frame, okay? This is an SCF. I don't want to complicate too much here, but what I mean is that in principle, what you have here is that this matrix is known, although, as I said, it could be affected by thermal deformation, so it has always, it requires always a calibration. But when you solve, for example, for the attitude using the star sensor, you are determining this matrix. So you need to multiply this matrix by this known matrix in order to have the attitude matrix. For our purposes, we are assuming that this is known, and basically when we compute the attitude of the spacecraft through some sensors, to star triggers, basically this is almost constant to the attitude. Okay, so we are excluding that there are important rotations from the star trigger reference frame and the body frame. Okay, so once we did this precision explanation of precise explanation of what we have to do when we have star triggers, what we need to do here is to define the angles lambda and phi. So these angles are indeed defined in the reference frame of the instrument. So phi, it is indeed, the lambda is the elevation, as you can see here, is the elevation with respect to the plane xs, ys. And phi is the projection of the line of sight of the stars in the plane xs, ys. So it's the angle between the projection of the line of sight to the ys axis. So it is this angle here. So the vector s can be defined by these angles, okay? It is important because this vector s corresponds basically to our vector w, okay? So our vector s is what in the VABA problem we call w. Another important, the other important, basically what we are going to measure, however, are not phi and lambda. What we are going to measure are the coordinates of the stars projected on the detector. So the detector will have a focal plane that is given by the CCD, so the charge couple device. So what will happen is that the star will project through a lens is positioned in a specific coordinates of the CCD. There will be U and V. But U and V are directly related to phi and lambda. So by measuring U and V directly from the detectors, we are able to determine S, and so our measurement W, okay? It is called S, as I said, because W in principle is the vector of the stars in the body frame. S is considered to be the vector of the stars, so the versor of the star in the instrument reference frame. To simplify the problem, we can assume that W and S are the same because we are assuming that the body frame and the instrument reference frame are coincident. In principle, you can have differences. Okay, that's the reason why it is written like the here.
Potrebbe ripetere quest'ultima cosa?
Yes, so what I mean here is that in principle, what you have is that probably it's better if I show you the figure of this spacecraft. So this is our star sensor. Okay, so the star sensor is fixed to the body of the spacecraft, but in general, so since the axes of this instrument are referred to the bore side of the instrument and the optical plane, so the focal plane of the instrument, you will have that this reference frame, so the star tracker optical frame, is not exactly coincident to the frame of the body. Because, for example, this platform here can be deformed by thermal gradients, or you can have deformation, mechanical deformation, and so on. So in principle, the vector S, so the star, is measured with respect to this reference frame. But if you want to compute the attitude of the spacecraft, your S, so the vector S of the star, the versor S of the star, is not exactly the unit vector that you need, so your W. Okay? What I am assuming here is that, so it's not really assumed because but when we are going to do the exercise, we can assume that this additional transformation matrix from the instrument to the body frame is, let's say, an identity matrix, okay? So we don't need to have an additional transformation. In real cases, you have to scale your S. Oh, let me write, maybe it's... So what I mean is that S, oh, sorry. What I mean is that our S here is basically not the attitude matrix, but is the rotation matrix from the ICRF to the SCF, so the star tracker reference frame, okay, of the vector V, that is the unit vector of the stars in the celestial coordinates. What you want to compute is W, and W is indeed attitude matrix times B, okay? So what it means is that to go from W to S, you have to do W equal to R from SCF to optical bench frame of the vector S, okay? Hope these explain what I mean. So if the reference frame from the star tracker to the optical bench frame is known, basically this matrix is known. So if you measure S, you are able directly to measure A, but you need to multiply S by this matrix that is the transformation from the optical bench frame to the from the star sensor to the optical bench frame. This explains a little bit better what I meant, or?
Sì, sì, grazie.
Okay, perfect. So let's go ahead, but basically here it's pretty simple because, so here you have a better figure of the sensor. So what is meant here is that you have your sort of telescope, so you have your lens. Here you have also the straight light shield. So it is a sort of a shield from the problems that we were discussing during the break. So for example, if you have a spacecraft around the Earth, not only you have a possible the possible interference due to the sunlight, but you can also have problems given by the Earth albedo. So usually these shields are used in order to enables that part of that field of view is protected. So for example, if you have your Earth here, you're able to look at the stars because a part of the light reflected by the Earth is indeed shielded by this part of the instrument. Same thing for the sun and so on. The optical lens, so the optics of the system that is also reported here is crucial because now we have to include what we have discussed about the stars. So basically, the optics of the system is designed by the need to improve the acquisition identification of stars. So what you need to do here is to provide a system that is going to look at the stars that you want to look. So for example, here you have this star, but let's assume that you have this one, this one, this one. So in principle, you are able to see all of them, right? The problem is that if all of them will be processed, you can have a problem called ambiguity. So basically the ambiguity that you are going to think that this star that you're looking from the catalog is this one. Because, for example, we can assume that these two stars have a similar magnitude. So if you have an error in the spacecraft attitude, this star can be confused with this one. So a way to avoid this ambiguity is to include additional properties of the stars. So for example, this is a star of spectral type B, and this one is the O star. If you have filters in your optics, you are not able to see the star because the signal from the star is filtered out, and you're only able to see B. So the advantage is you're limiting the number of stars in order to avoid ambiguities. On the other hand, as we are going to see later, that could provide problems in the identification of the star. For example, there is a method that is called angular separation of the stars. So you're going to see that it's better to have a larger number of stars in order to have an improved identification and acquisition of the stars. So the optics plays a crucial role because it enables these kind of things that I was discussing. The other crucial role is given by the CCD, because the CCD matrix, as I said, is a charge-coupled device. So it means that this device consists of sensitive elements that enables to detect the presence of a star, as you can see here. So basically these sensitive elements that are called pixels are able to detect that you are seeing stars in this portion of the CCD that, as we have said before, corresponds to coordinates on the focal plane. So we have these coordinates u and v that are translated in phi and lambda, and so in our versors S. Said that, why we need to design the charge coupled device in a fine with a larger number of pixels? That could be one of the questions that could be asked later. So we need to determine a larger number of pixels in order to have a better accuracy in the altitude determination. So basically, if you are able to increase your number of pixels, you are able to increase your, so you are able to have a finer a finer partitioning of the area of the sky or the region of the sky that you are looking at. So assuming that you have a field of view, as is written here, 5 degree by 5 degree, right? And you have a CCD with 500 pixel by 500 pixel. So 500 by 500. Well, it is easy to be demonstrated. So it's a very easy demonstration to determine the accuracy that you can get from this CCD. So you are able to divide it by, for example, 5 degrees to 500 degrees. Sorry, to 500 pixels. That means that you have that each pixel give you 1/100 degrees in terms of arc seconds. So this is the resolution of 1 pixel, okay? This is 1 pixel. In terms of arc seconds is, if you do 3600, so 3600 pixels, you have 36 arc seconds. So a design of the CCD in this way give you a resolution of 36 arc seconds, that, as I said, is really poor. So you need to increase your field of view, or decrease your field of view, or increase the number of pixels. If you increase the number of pixels, you are able to have a finer scales of these pixels, so you're able to detect the stars with a finer resolution. So why we need a finer resolution? So basically, the design of the field of view of the star tracker and the number of pixels give you the accuracy. So you have to find a specific amount of field of view that you need and the number of pixels in order to determine, for example, a milli-arc second accuracy. You can do the math, but you can understand that you will need very tight field of views and very large number of pixels. Usually it's better to have a smaller field of view. The problem is that if you do a smaller field of view, you're going to look at a smaller portion of the sky, and you will limit the number of stars that you're going to look at. So that means that when you do the first part of the method, so the star identification and acquisition, there is a major problem. So if you have few stars, you can have very strong problems with ambiguity. So let's assume that you have your you are loading your okay, so this is the catalog that is loaded by your spacecraft. Okay, so for example, from your catalog you have that the position of these stars is O. Okay, so it means that at a certain time you are trying to determine the position of that star. So you are loading, so you are saying that your instrument is looking at that portion of the sky. As I said, you are able to do that, for example, if the gyroscope provides you a preliminary altitude determination of the spacecraft. But of course, those have a very large errors. So in reality, what your instrument is looking at the same star here that you have in your star catalog. In reality is here with a versor S, okay? The versor that we have measured here. So there is a discrepancy, right? So if you project so basically what you can do, so what I would like to do is to show you. Okay, let's do like that. So the first method that you can use to determine if you are able, to identify a certain star is doing the what is called direct match. So basically, you superimpose this position of the star in your catalog to the position of the star that is seen from your instrument. So you compute the distance. That's the reason why I would like to do that. So what I would like to do is, let's do it like that. So you are going to compute the relative distance between what is assumed from your star catalog and the vector that you are actually seeing from your instrument. So assuming that the two stars are exactly that, you are computing this d, and you have to compute that this d, so this distance between these two vectors is lower than epsilon. What is the problem with direct match? The problem with direct match is related to the fact that you can have a strong ambiguity in the definition of the star, because it can happen that if you are looking only at two stars can have similar properties for magnitude and also spectral type. So what I mean is that what you think the unit vector O is giving you from the star catalog is not really referred to the star that you are looking at from your star sensor. So that would induce significant errors because you are using two different stars to identify basically identify the position of the spacecraft. So this O is not really O, but it would be, for example, an O prime. Okay, so it is another star. So you are comparing two stars that are not exactly the same. So this method indeed can provide significant errors. The best method that you can use is the angular separation match. The problem is almost the same. The only difference is that in this case, in order to avoid the problems, you are not looking at one single star. You are looking at O1 and O2. Okay? Same thing here. Assuming that you have an error in your attitude, so the stars will be S1 and S2, so you have a rotation, for example, like that. And what you're going to compare is not the distance between O1 and O2 and S2, S1, but you're going to compare the cosine of the cross product between these two vectors. So you do the cross product between these two vectors and these two, and you compare these D1 to M. So you compare the relative distance between the angular separation between these two stars. Why this is useful with respect to this one? Because if in case of one single star, the ambiguity could be a serious problem. When you have multiple stars, or at least two, the relative configuration between the two stars is rare, and that's the reason why this is one method. One other method that we can use, it is called the polygon match. So let's write that here. A third method is an extension of the angular separation match, but it's called the polygon method. Polygon method is an extension of the angular separation in which you have, for example, let's do 4 stars. Okay, this is what you have seen from the okay, so the okay, so let me do like that. What I would like to I'm trying to so what I like to do is that when you try to compare these two, in order to have the same configuration. So what I mean is that here you have O1, okay? O1, O2, O3, O4. Here you have something different because here will be S1, S2, and S4. So if you use multiple stars, so this polygon approach, by computing multiple relative distance from the stars, you are not able to have ambiguity because you are sure that all the configuration, this particular polygon configuration that you have is unique, and you are able indeed to provide the best knowledge of the attitude. So I would conclude here, since it is already 2 p.m. But next week we are going to see that what is done after that. So what we have seen so far, we have seen the design of the star tracker, and we have also seen the star catalog upload and the star identification and acquisition. So the three techniques that are used to do that. Once you are able to know that these are from this comparison, that you are looking at the portion of the sky that you need, now you start to use your vector S, for example, in the Quest algorithm or in the extended Kalman filter, by using the star tracking. So once you know that you are looking at the right portion of the sky, so you have done the match between the stars that are coming from the star catalog and the stars that you are looking from the sensor, now you are able to start your tracking of the stars. And that will give you the every single time the evolution of the vector S that you need to use in your processing. And so the third and fourth blocks are tied together, because once you're able to track the stars, as I'm going to show you next week, you're also able to have every single time a different estimation of S, and so determine the altitude every time. So we will see also the instrumentation and the source of errors that are given by the sensor itself and, for example, the catalog. So I would conclude here. So let's stop the records, the recording on the video, and let me know